I've had a couple of questions on the setup to measure the power consumption of the cheap soldering irons. I think a short video will do a much better job of presenting the setup over trying to describe it in writing. I use two different setups to measure the power, one with 2 meters, 1 meter measuring current and the other measuring AC voltage. The other setup using a scope with one channel reading AC volts and the other channel measuring the voltage across a 1 ohm resistor, yielding a current value. One reason I didn't give much detail about the power measurements is because these irons run on 120 volt AC line voltage. This thing here is important for both the ways I measured the power. This is an isolation transformer. Now you won't find this model anywhere, as this thing is probably around 40 years old. Well, might find it on eBay. It has some taps on it, so its output voltage can be adjusted somewhat. But its important function is to isolate the 120 volt AC it outputs from the 120 volt AC line voltage. While not absolutely necessary for the measurements with the 2 meters, it does increase safety. But with a grounded scope, this isolation transformer is a must-have for the scope measurements. While this isolation transformer greatly increases the safety of taking the measurements, we are still dealing with 120 volts AC, and there are dangers that come with that. And you need to know and understand those dangers when measuring AC line voltages. And this is not a tutorial on those dangers. This is just how I did my measurements. For the meter setup, I have the isolation transformer and a power cord with banana jacks on the end. After the isolation transformer, there is no hot or neutral terminal. There will simply be 120 volts AC across the banana jacks. One meter will be used to measure AC volts, and another meter will be set to measure AC, in this case milliamps. The load, aka the soldering iron, will plug into a standard AC outlet. To interconnect everything, I'm going to use some stackable banana plugs. I will use some alligator clips to connect to the AC outlet, and it doesn't matter which lead goes where, as there is no neutral or hot. And of course there is no ground being used. The current meter has one of its leads connected to one of the AC banana jacks. The other terminal of the current meter will connect to the AC outlet. And I will set the meter to AC milliamps range. The other terminal of the AC outlet will connect to the other AC banana jack. That will connect the AC out of the isolation transformer to the AC outlet with the current meter in the path. Now for the voltage measurement, I will set the meter to AC volts, and the meter terminals are connected across the AC outlet. After plugging in the isolation transformer, you can see I have 122 volts on the AC outlet, and with nothing plugged into the outlet, have 0 current flowing. Without getting my hand across the AC outlet terminals, I'll plug in one of the cheap irons. So with the iron off, it pulls a little under 4 milliamps. And when I turn it on, there is a large spike of current. Then it settles down as the heating element gets hot. Dropping pretty quickly to under 300 milliamps. And if I multiply the current by the voltage, I end up with around 35 watts of power. And this setup should give pretty accurate values for any resistive load. For the scope setup, things are a bit more complicated. One reason is I don't have a current probe for the scope. That means measuring the voltage across a resistor to ascertain the current. I have my isolation transformer and a cord with banana jacks on the end. That will supply 120 volts AC. I have an AC outlet that the load, aka soldering iron, will plug into. One terminal of the AC outlet will connect to one of the banana jacks from the isolation transformer. The other banana jack from the isolation transformer will connect to one side of a 1 ohm resistor. The other side of the 1 ohm resistor will connect to the other terminal of the AC outlet. I now have the 120 volts connected to the AC outlet. I'm using two channels of the scope, one to measure voltage and another to measure current. One complication that comes with that is the ground terminal of both channels are connected together and in most cases connected to earth ground. I have the one channel set to 100 volts of division and that measures the voltage. And I have the other channel set to 100 millivolts of division. So 100 millivolts across a 1 ohm resistor should equal 100 milliamps of current. The resistor AC outlet connection will be the common tie point. This is the connection for the ground leads of the scope probes. This does have the effect of now tying one side of the 120 volts AC to ground, so it does increase the danger of dealing with the 120 volts. The voltage channel will connect to the non-resistor terminal of the AC outlet. The current channel will connect to the resistor AC line connection. With this setup, the current and voltage are out of phase, so one of the scope channels will need to be inverted to get the proper readings. So with it all hooked up, I will power up the isolation transformer. No sparks or smoke is always a good sign. With nothing plugged into the outlet, can see the AC voltage is running about 123 volts. The 10 millivolts is not really 10 milliamps, it's just noise being picked up from all the wiring. So plugging in the iron greatly increases the noise, but can see the little bit of current the iron pulls right at one of the peaks. Of course, the iron is turned off at this point. Now when the iron is turned on, the current is large enough to saturate the input. But it drops as the heater in the iron heats up. And it reaches a point where the control circuit in the iron turns the power off for a short burst. Trying to maintain a fixed tip temperature, just doing a poor job of it. The meter setup really didn't reveal the short power interruptions of the heater current, so it is worth the extra work to use the scope sometimes. At this point, I can just multiply the channel 1 volts by the channel 2 volts and I will have the power. But the scope can do a lot of the math itself. If I bring up the math menu for the scope, I can select channel 1 as source A and channel 2 as source B. The math function I want is to multiply A and B. I'll set the scale at 20 units, and the units in this case will be watts. Can see the power is at twice the frequency as the voltage waveform, as the power is supplied at every peak, both positive and negative. Also can see that the peak instantaneous power is a bit over 80 watts, about the rating of the iron, but not a good indicator of the heat from the iron. The scope can also measure the waveform math channel. I'll select the Math 1 channel and voltage average. The iron is hot enough now it's hard to read a constant value. So if I select a single sweep when it's powered on, I can get a stable view of the power consumption. And I get right at 34 watts. And that is how I set up to measure the power the soldering irons were pulling. Thank you for watching.